in some sense, will continue the previous topic when, as far as I know, there was a talk about abstract state machines. And then, so just two main words here in the title are distributed systems and modeling. So I guess you know what is a distributed system. That means that there is no supervision, no centralized control. And of course, there are plenty of examples starting from nets of different kinds, but also multi-process systems, different kinds of productive systems where agents interact, robotics, everywhere. So, of course, it is very important to organize the work of such system, and it is not easy to do because people think sequentially, and so just to understand what may happen when we have distributed systems, even if they are not very complex, is not an easy thing to do. And then, of course, we do need modeling because we are interested in ensuring correct behavior of such systems and how to verify them, how to be sure that algorithms we use are correct and that we have organized our system in the right way. Of course, if we have a complex system, we should start with modeling. So it's not a good idea first to construct a system and then to check whether it is correct or not. Of course, first to have a model and then to develop a concrete system. One more point is that when we are constructing models, of course, we abstract from some aspects of the system. And then we can concentrate on really important things and in many cases prove that they are correct. And then we may be sure that when we implement this model, we have much more chances. Nobody can guarantee anything, but we have much more chances to have a good and robust system. So, as I told, it will be in some sense a continuation of the previous talk. I mean that I will speak about Petri nets, and Petri nets are also, to say, automata-based models. It is a formalism in some sense, extending of finite state machines. And so what shall we speak about today? So the agenda is as follows. I start with some introduction and initial examples, and we'll speak about so-called classical Petri nets. Then I will speak about the extension of which is called colored Petri nets, and it is a kind of high-level Petri nets. When we have finite state machines or classical Petri nets, we are dealing with, we are aware of control, the behavior. So what actions can occur? But also sometimes we are to take data into account. And also you have such an example in the previous talk, I guess. So now we'll speak about modeling distributed systems with colored Petri nets. So I'll start with some introduction and very initial modeling example. And when we have a distributed system, so it consists of several So we can call them processes, agents, threads, so just or even separate devices. It depends on the application area. Each of them has its own behavior, but also, of course, they do communicate. So we start with this modeling control flow, and imagine we have two agents. One of them is sender and the other is receiver, and they have very simple behavior. So sender may send a message. So it looks like here minus means that he sends, and then switch to the state A2. And then when he receives acknowledgement, he returns to his initial state. The receiver has a symmetrical behavior, so it may receive a message, plus means receiving, and then so send acknowledgement. If we model them separately, so we can consider them as finite state machines, finite automata, but of course the important thing that they do communicate. So here we have just two separate finite state machines. Then, so to make petriness from these state machines, we are doing very simple thing, you see. So just we add transitions explicitly. So now we have a special node for sending message and for receiving acknowledgement, and here symmetrically. And also, so for a finite state machine, we always have a current state. And here we have two finite state machines. So we have two nodes marked as a current state, and we put a token here. So a token in A1 and a token in B1. And now how to organize communication? There can be two kinds of communication. The first is called synchronization. So synchronous communications mean that they fire these transitions simultaneously. And then how do we model it with petriness? We just have a common transition, which is done simultaneously by two agents. So for a finite state machine, so a transition can fire or can be done if we have a token in the input place here for acknowledgement. If we have a token here, then acknowledgement can be fired. But here to fire this synchronous communication, handshaking, they should be both ready simultaneously, and after firing, both change their state. So just initially we have a current state where we have tokens in A1 and B1. After firing rec, we have a token in A2 and a token in B2. So we can model synchronization this way. It also could be that our sender and receiver do not communicate synchronously, but they use some channel for messages and for acknowledgements. And then to model it, we add one more local state. So now these states become local states, and global states is described by token distribution. So now here, when a sender fires transition, sending, then he changes its state and adds a token which designates a message in this channel. receiver, when there is something in the channel, may fire this transition receive, and then so just this token message will be consumed from channel 1, and the receiver will come to the state, local state B2. So symmetrically, we can organize another channel for acknowledgements, and then we have this system. And what have changed also, so in comparing with finite state machines. So now it could be that the sender has sent, so not here. So he's waiting for sending a new message. He's to receive an acknowledgement. But so just if, so just theoretically, so just not for this system, but it could be that channel contains more than one token. And that's the main difference with a finite state machine. So, of course, I do understand that we exist online and all that, but I would be grateful if you ask me questions, not waiting the end of the lecture. Then I feel that you're with me, and also you will not postpone your questions till the end when it may be not so convenient to do, maybe a bit late to ask. So then do not hesitate to interrupt me and to ask questions and to give comments. Well, and also if somebody of you would like to switch on your video camera, I hope the system will not go down, because then I have at least a bit of feedback. Oh, thank you very much. Thank you. Fine. And then at least I see that you're with me. Fine. Then I think that it is a very easy example, but it includes main principles of Petri nets. So what do we have? So of course, some historical comment. Petri nets, so Petri is a name. So Carl Adam Petri introduced this formalism, and he, to say, invented this way of modeling when he was a PhD student. So just there is even a story that he invented such so model schemes when he was a schoolboy, when he was studying chemistry, just to draw chemical reactions and to visualize it, to make it easier to memorize all these rules. And then when he was a PhD student, he prepared his thesis, so which was so named Communication mit Automaten. And so it's communicating automata, exactly what we studied with. And what is fine with this formalism, so just it is like you know, finite state machines. It is very universal. So it may be applied to hardware, software, production system, business process, everything. So we do have distributed system and communicating agents in many areas. And here we have the very essence of behavior and communication. And actually, when we organize such system, of course, so just working with data is important, but here not computation is important, interaction is important, and it is the most difficult thing to model and to follow. And here we can abstract actually of data, just maybe have resources as some finite number of tokens in some place, and this allows us to model very essential aspects of this distributed behavior. So then what is a Petri net? First of all, it is a formalism for modeling and analysis of concurrent, distributed, parallel, non-deterministic, and non-determinism is a formal way of looking towards stochastic, and then it has a formal semantics. It is mathematically defined, and that's very important. So it has formal semantics. Then it is a graphical tool, and that is very important because you can easily explain the model to somebody who is not very sophisticated in mathematics or something, because it gives us a good visualization like a finite state machine. And another important aspect is that it is a mathematical tool. So having this formal semantics, we can actually prove properties for such models. And of course, that's very important, especially for different kinds of critical systems when we are to deal with this very complex behavior. Then I'll speak about modeling today, not about verification. Of course, there's much may be said about verification as well and proving properties. And now just how to represent distributed behavior. So we can summarize modeling principles of Petri nets like follows. So first of all, it is a graph, and we have two kinds of nodes in this graph. So we have circles, and they are called places, and they can store tokens for presenting a current state. And then, so just these places can be used to model local states of our system, like we showed local states of agents in the previous example. They can be used to model different kinds of logical conditions for firing some transition, for doing this or that action, and also post condition, what will happen, what will change after the transition firing. Also, we may have several tokens in one place, and then they can be considered as resources needed for doing this or that action. And these are resources consumed or produced by transitions. And also it may be different kinds of input and output signals. It may be buffers. So just very different things. Another kind of nodes. So they are drawn as squares, and they are called transitions. And they are for events, activities, tasks, jobs, signal processes. So they represent dynamics. And also, so it is a graph. So arcs link places to transitions and transitions to places, and they represent different kinds of causality, or so just direct, maybe transferring goods from one local place to another. So the graph, which represents a Petri net, is a bipartite graph. So it is not allowed to have an arrow from one place to another or from one transition to another. And the intuition after this is as follows. So transitions are reactive elements, and states, local states, places are passive elements. And if, for instance, we would like to model net of two computers, and we should like to show that computer T1 sends some information to computer T2, it would be not a good idea just to draw an arrow from one computer to another, because actually there is always a communication channel in between. So it can't be, so this is just an action, this is also an action, and then there should be a result of this action which is consumed by the second computer. So these principles are very important and they help us to construct so adequate models, I would say. Not to forget about this channel, for instance, here, and also you see we can add the third computer to this channel. It is easy to be done, and here where to add the third computer.
I have a question.
Yeah, please.
So in this case, can you also model so that you have, let's say, a probability to go to different states and so on? Or is that not possible with Petri nets? Let's say you're in a state and you have some transition and the outcome is, it can be different outcomes. Can you model the probability?
So there is a basic formalism where there is no probability or fuzzy or anything or time, for instance, but there are many different extensions of this basic formalism, and there are stochastic Petri nets, fuzzy Petri nets, time Petri nets, and so on. And so the point is that when we have this basic formalism, then we still have decidability of some important properties. You know, for finite state machines, almost everything is decidable, but they have a finite number of reachable states, and then it is clear that you can just use model checking and just systematically check all reachable states if. So it's just of course there is state explosion problem and all of that, but still. But for Petri nets, of course, you may have, generally speaking, unlimited number of tokens in one state. So these are systems with infinite number of states, but many important properties are decidable for Petri nets. For instance, reachability is decidable, or boundedness, to check whether the reachability space is finite or not. So just you can check if it is finite, you can apply model checking. Of course, all these algorithms are rather complicated, and just to apply them directly, so just you don't need too much resources. But still, if you have decidable model, then it means in practice, so just it's like a rule of thumb, you know, that you can do something with such models. But if it is just undecidable from the very beginning, you can't do much. And even so, just in general case, the algorithms are very complex. I mean, so just computational complexity, but so just there are special subclasses, special cases when you can really apply these proof techniques and model checking techniques and such things. When you add time, stochastic, fuzziness, anything else, of course, it becomes much more complex. And then, so just such extensions are mainly used for simulation, not for proving. But you can prove something for the basic Petri net, which underlies this model, do something like this, and this is also very helpful. So, of course, different extensions are used when you have real system, and then you do need something so specific to add to this basic formalism, like finite state machines. You know, they are also, there are many different extensions of finite state machines. You can add also time, probability, different aspects. And then, of course, still we have these so basic core, I would say, formalism, and when you understand so just how to deal with it, then it helps you even in such case when you can't do proving or verification directly. And now I come to formal definition, which is I think you also can guess what is it. So just we have a graph actually. So two kinds of nodes, places, finite state of places. We have a finite graph and finite set of transitions, so they do not intersect. We have this arcs, which is called flow relation. So it is a directed graph directed by Petite graph. And so also we may have weight functions. That means so just to not to draw multiple arcs, we just can add weights to our arcs. And concerning the state, then it is a state is called marking. Marking is a function which maps places to natural numbers, including zeros. That means it designates how many tokens are there in each place. And there is an initial marking, which so just an initial state for this system. Then that is the definition of, to say, syntax graph. And now we are to define dynamics for such model. And dynamics is defined by so-called transition firing rule. So you remember that transitions they're represented by squares, so special nodes in our Petri net. And then we say that a transition is enabled in some current marking in some current state if for all input states, for each input states, and input state is a state from where we have an arrow to this transition. Yeah, we have enough tokens to fire, and how many tokens is needed is defined by the weight of the corresponding arcs. So we may draw just an arc and put so just multiplicity to this arc weight, and then say that we need 2 tokens in this place and 1 token in this place and so on to fire this transition. So it may be conditions, it may be resources, so just interpretation may be different kind. And after firing, we receive a new state, a new marking, and then all tokens which were needed for enabling this transition are consumed, and new tokens are produced, and the number of tokens produced depends on the also weights of output arcs. So I have an example, and here it is a chemical reaction. Maybe Petri was drawing something like this. Of course, it is just virtual reaction. So just in chemistry, so it is not so easy just to obtain water from molecules, but still. So just what do we have here? We have here, this is a place for hydrogen. So just now in the current marking, we have 2 molecules of hydrogen and 2 molecules of oxygen. And this transition, so just it is for obtaining water from these molecules. And for that, we need 2 molecules of hydrogen, 1 molecule of oxygen, and as a result, we have 2 molecules of water. So these weights designate the number of tokens consumed and produced. So after firing, now this transition is enabled. It can fire because we have 2 tokens here and we have 1 token here, enough. So after firing, these 2 will be consumed. This here 1 will be consumed. We still have 1 molecule here, and we now have 2 molecules of water. That's the rule of transition firing. Note that since it is a distributed system, then so firing of a transition doesn't change tokens, doesn't touch tokens which are not in the places adjacent to this transition. So we have this locality property. So when we have a distributed system, then of course each agent can interact with only with those agents who are close to him. And then we have this firing rule. One more thing is that when we have a Petrinet and we have current marking, then it could be that several transitions are enabled simultaneously. Then how to define the next step? The next step is defined as a non-deterministic choice between these enabled transitions. And then it is it is a common thing for concurrency. Of course, it could be that two transitions are enabled and they do not compete for any resources, though they can fire completely independently. And then we consider them as concurrent transitions. Or they may compete for resource. So just like the first transition will use this token or the second, and then we have a conflict. And of course, when we have a conflict, it is a choice, so it is clear, like actually in finite state machines. But when we have concurrency, so of course, we would like to model this concurrency, and we define it as non-deterministic firing of one or another transition. But this is a common way in concurrency theory to look at, so just to define so-called interleaving semantics. So imagine you have two independent actions, A and B, and then how to model their firing. Of course, you can say, oh, well, let them fire simultaneously. But you know, in distributed system, there is no notion of simultaneously. So if you are just in the internet and your mate also in the internet, you do not do anything simultaneously, though you are working concurrently. Yeah. So just also there are even principles of physics which say that you can't synchronize everything. Yeah. So then we just know that they are independent. And how to represent it? Of course, we could represent it as a flow. So we can draw a behavior as a graph. We have two independent firing of two actions. But it is rather complicated to deal with. And another way to look at it is just to consider that when we have two concurrent actions, A and B, then they can fire in any order. And if they do not have conflicts, then, so if A fires, after that B can fires. And if B fires, then A can fire. So we model this concurrency as non-deterministic choice between two sequential runs. And what is important that for many properties, actually for most important properties, so what is true with this interleaving semantics is also true with so-called true concurrency semantics when we consider this independent firing and more so just as a flow of events. Of course, there are some cases when true concurrency is important, especially when you take time into account and all such things are rather complicated. But in many cases, for instance, when you analyze reachability, safeness, then so it is enough to consider this interleaving semantics. That's why mainly, so this semantics is studied. Of course, you can also find so definition of true concurrency semantics for Petrinets and so on. Also, for hardware systems, there is even another semantics which is used when if several transitions can fire simultaneously, so there are enough resources, then they fire simultaneously. Of course, there is non-deterministic choice of how many of them, if it will be maximal, number, then it will be already so just a power of universal computability, so too much in some sense. So all this stuff is well studied and is rather interesting. So concerning these fundamental principles of computability. So, but interleaving semantics is good and enough for many applications, and mainly such semantics is considered. So, just to show you that a finite state machine actually can be considered as a special case of a Petri net. And here, you see, here you have an example. And this is a finite state machine. We could just forget about this transition and just have arrows. It will be a finite state machine, non-deterministic. Yes. Here we have added transitions, and now it is a Petri net, but it is actually behaves like a finite state machine. So it is a very restricted subclass. Then what can we model with Petri nets? Of course, we can model choice. So just finite state machines are enough for that. Here we have a state where we have one token in this place start, and there is a choice either to fire here 5 cents, just what coins to use for buying candies, or 10 cents. There is a non-deterministic choice. It could be also conflict or decision, of course. But also we can model concurrency. So just what do we have in this example? We have, so just here, we have a current state which could be obtained, maybe initially there was a token in P5, then T1 fires, and it puts one token in P1 and one token in P2. So in finite state machine, it looks like tokens are transferred from one place to another, but here not. You see, there was one token, now there are two, so it's just changing the marking. And now it means what this transition is like parallel fork. Yes, so just we start two independent branches, parallel branches, and now T2 and T3 can fire independently, concurrently. And after that, so just after firing T2, we have a token in P3. After firing T3, we have a token in P4. And now we can fire T4, which is we join for these two branches. So we can represent such behavior, of course. One more example. This is a communication protocol. And of course, Petri nets are very good for modeling such algorithms. This is a very simple one. So we have two agents, send and receiver. Now they are drawn a bit nicer than in the previous, the very beginning. Yes, so concerning sender, it may be ready to send here. Then he's sending, he's waiting for acknowledgement. Then here he has received an acknowledgement, and he may stay here as long as he wants. And then if then there is a need to send something else, then he comes here. Yeah. To send, it is to have this sending enabled, it is needed that there is a token in ready to send. A receiver has a symmetrical behavior, but to receive, he is not just to be ready to receive, but there should be something to receive. So there should be a token here and a token in buffer. Then receive is enabled, and then here message is received, and he's sending acknowledgement. Then here goes a token with acknowledgement. Here goes a token that, so this is, you see, they have different meaning. This is like a local state, and this is these are resources. Here we can easily prove that, so there can't be more than one token in each buffer. One more example, just to show that in different application area we can use pattern nets. And here we have data flow computation, and so just we can model is as some transitions are independent, and some have so causality relations, so just should be done one after another. So we can, of course, represent such things. Maybe data flow are more easy, but still. This is one more example, and there is a very so universal, I would say, problem in distributed system when here two processes or several processes are sharing some resource, then there may be some constraints on sharing the resource. For instance, if it is some value in database, and it can't be that two resources are writing simultaneously, or it is not allowed that one is writing and the other is reading, because then it leads to bad consequences. And then so there should be some discipline that only one resource should have an access, or one process should have an access to the resource at each time. And this is called mutual exclusion problem. So mutual exclusion can't be more than one. And here, so just a very simple algorithm or model. So the simplest one, you know, so just what to do to use a kind of a flag. Yes, so just if we have a token in B, then this, it is called critical area. So just it is, so just the access is allowed, or the process can enter to its critical area. And then so just if it, for instance, A can fire a small a, come here, and then after firing B, so just now it isn't its critical section, then there is no token here, this can't so just get access to its critical section and so on. So to check that this process so is okay, that mutual exclusion is okay, that means that in each reachable state, there can't be that we have a token in C and in G simultaneously. So it's rather easy because it is bounded and we have a small reachability graph. Also, there are other techniques to prove that it is safe even without constructing reachability graph. And of course, here, so just one more thing, when we have, we can consider sequential runs for such system, yeah, so different variants of non-deterministic behavior. And here we have it like ADE means that we have a token in A token in D, and a token in E, then A fires, we come to this state and so on. And there are many sequential runs, actually infinitely many, but what is good that so just since the net is bounded, so just in each reachable state, there is a limited number of tokens, or the number of reachable states is finite. So of course we can represent it with a reachability graph. It will be finite, and our infinite behavior are paths with loops in this graph. So we can analyze such graph to be sure that everything is okay. For instance, here we can just check that we do not have reachable states where we have C and G simultaneously. So this was a very brief introduction to classical patronage. And I also want you to say a few words about a very important extension of such of patronage, which is called sometimes high patronage, high-level patronage, and high-level patronage. So there are different variants, but the most popular are colored patronage. And with here also, just I'll show you an example which illustrates how it works. And we start with a very famous dining philosophy example, which was so introduced by Dijkstra. And the story is as follows. So we have a round table. Also, just it could be, I remember that Dijkstra had so just one dish, but it doesn't matter. And we have philosophers sitting around, yes. And philosophers have very simple behavior. Each philosopher can either think or eat. And for eating, and they eat spaghetti in this story, so he needs 2 forks. And they have, you see, so here in the picture, there are 5 philosophers and 5 forks. So they share some forks. Each philosopher shares a fork with its neighbor, left fork with left neighbor, and right fork with right neighbor. And so each of them, so from time to time, so a philosopher wants to eat, then he's taking his forks, if they are available, eats, and so on. And this example is very good because it illustrates many important things connected with distributed behavior. For instance, so if philosophers take forks not simultaneously, but in turn, so just, for instance, first left one, then right one, if one of them is not available, it just waits for it, then there is a possibility of deadlock when, for instance, each philosopher takes its left fork, and then it is a deadlock. Another thing is a very important notion of fairness for such systems when we have processes sharing resources. And fairness means that so no process is ignored forever. And here, the generally speaking, could be a behavior when so just some philosophers say this one and this one are eating in turn, and this one can't get access to its fork. Yeah. So, and this example introduced by Dijkstra in I think so, it's just between 70s and 80s, very late 70s. So just it is still one of the most popular to illustrate very different things which people introduce for dealing with distributed systems. Then, so now we would like to construct a model of this system with patronage. And we start with modeling behavior of just one philosopher, one separate philosopher. So just what do we have? We have local states. Here, so just he's ready to start eating, yes. So he takes right fork. This is a right fork for him. This is a left fork. He's ready to take right fork. Now here in this state, he has a right fork. Then taking left fork. Now in this state, he has both. And then so just in some time, he's finished with eating, and then here he's thinking. Yeah. So this is behavior for one philosopher. Now we combine it into a system for several philosophers. So here are 3 philosophers, just to not draw too much. So Now you see each fragment is exactly what we had before, but they do share forks. And we have all these possible behaviors here. So, of course, it is a nice model. We can simulate, we can prove, we can do different things. But what is not nice? It is not nice that if we have 5 philosophers, for instance, then we are to construct model from scratch and to verify it from scratch, and that is not nice. And also, you know, so just we have quite the same fragments 3 times. So just it's not nice. Each mathematician would like to make a kind of parameter or something to make it more readable and more easy to understand and to deal with. So, and we'll do it like, so just it is done for high level pattern nets. So we do it step by step. First of all, the first step, so just here in our example, we have separate place for each fork. So forks are so resources of the same type. So we just join them into one place. But of course, we should distinguish them. They can't be black dots no longer, because so just depending of what number is this fork, so it depends which philosopher has access to it. So that's why it is called pattern net. So just we color these tokens. Of course, you can just put numbers, but the name goes from this. So we are going to join these forks, but then also it is important that when now, so just all these arcs will go to the same place, and we should distinguish them, because philosopher number 1 uses forks number 1 and 2. Philosopher number 3 uses forks number 2 and 3, and so on. So what do? We put numbers on arcs. So it is just, before it was so just multiplicity 1, so just nothing. But now we put a type or a value, actually, not a type, a value of which represents this or that fork. And what do we get? Such a nice picture. Now it is a bit smaller. So we have forks number 1, 2, and 3, and we have numbers here. And now it is clear that for philosopher 1 to take fork 1, it takes fork number 1, and so on. Yeah. Then we go further. And then, of course, we also have now join philosophers. We have one place for philosophers. And now what do we have? You see, instead of, since now we do not have separate philosophers, then we have just a variable here. And we have here philosophers. Philosophers are represented by numbers. Forks are represented by numbers, and arcs have variables which connect this. And what is the meaning? I'll switch to the next, maybe here. I'll do it step by step. So what does it mean? So now this, to say this variable may be bounded with a concrete value. And depending on this, it may fire with this value or not. So for this, now for this, for instance, philosopher finished, when he returns 2 forks, there may be different modes of firing. It may fire returning forks number 1 or 2, or number 2 or 3, and or 3 or 1, and then So depending on the number of philosophy here. So if we consume a token number P here, then we return a fork number P and a fork which is computed here because of round, you see. For 3 it will be 1, otherwise it will be P plus 1. So we can compute it, and it is done with binding this variable. So just what modes are possible? It depends. So just what tokens do we have in the input args? Here, if there are philosophers number 2 and 3, so it's just not possible actually, but if then, so just it can fire in 2 modes, either with mode P equal to 2 or mode P equals to 3. And then, of course, as usual, we have a non-deterministic choice. Who will be the first? Well, so since we have here variables, we have here values of different types. Some of them are philosophers, some of them are folks. Yes, then we also have now a declarative part together with this net. So we describe colors. Colors are so color sets. It's called types, actually type sets. And then values and functions we use and types of variables, and we can use these variables here. So that's how a color Petri net looks like. And so this is usually written, so not usually, so for color Petri nets for CPN in ML functional language. Yeah. And this is, yeah. So once more, to be precise, I'm to define accurately firing rule for this case. So we have a transition. We have 2 input places. We have 1 output places. So we define firing in different modes depending on binding on the of variables. And then it is there is a misprint, sorry. There should be P, not F, because there should be the same variable. You see, so just this value should be the same with this one and this one. And then, so just informally, sorry, it's okay because it is written, there is a guard that they should be, sorry. So it is done to make it more nice because they are of different type, yeah. Folks and yes, so F should be equal to P. And then, so just we define binding where, for instance, P is equal to F and equals to 2. And then it means if we have here, so just a token number 2, and here we have a token number 2, then philosopher number 2 takes fork number 2, and now he's going there, sorry, and the fork just vanishes for some time because it is used. Yeah, so it is not shown anywhere. And also what is important, you see, when we have these variables, so we bind variables on args adjacent to this transition. So we have this locality. So this is result of this. Yep.
So here we have like a restriction that a philosopher can take only the fork with the number the same as the number of this philosopher, right?
Yes, this is it. Yeah. So generally, so just to explain what is written here. Here it is written the current state that all forks are available. All philosophers here, they are all here. And after firing, we have that here we have still, this is just a sum for multisets, union of multisets. So just here we have after firing, so the second fork goes away, and we have fork 1 and fork 3, and here we have philosopher 2. And here philosophers 1 and 3 are still here.
Okay, and for the left fork, it will be different. So there will be like P equals F plus 1 or something like that.
So just to, we can write here, even so just here it is, it takes left, and for left it is always just the same number, and for right it will be, you see, this is the definition of this function, and we can write, we can use here in expressions not only variables but expressions with functions defined here, or anything you want actually. So of course there should be some reasonable restrictions, and what is, and we have got these also conditions on these variables.
Okay,
and now what is nice, if we have such a model, you see here number of philosophers is 3. We can just change it to 7 or 100, and it will be the model. So we have a parameter here. So we have one universal model for this, for any number of philosophers. So colored Petri nets were introduced by Kurt Jensen, and there is a book, and there is a tool which is more important, so just supported for many years and actually used not only so just for research, but also in industry. So just I think maybe one of the most used PetriNet tools. And so this is how it looks. This model, so you see, so just the declarative part is not shown, but here we have, this is initial state. So what do we have here? And you see here also even integer numbers are allowed, and here we have strings, so different kinds of values, different types of values are allowed here. Of course, there are some details connected with what do we use. So just, and I'll tell a few words about it. So this is just a reference, and this is at Aarhus University, Denmark. So it is supported, though Kurt Jensen has retired, but they do support it still, and so just has so several decades history already. So there are also possibilities to make analysis with this tool, not just modeling. And then to see a few words so concerning formal background, so just and returning to decidability and all such things, what can we do for colored Petri nets? So it is clear that when we add arithmetic, so when we add natural numbers and the operations on natural numbers, then we have such all so power of Turing machine. We can compute everything, so nothing is decidable. But if we can use only finite types, so type sets are finite, then so when we compare expressibility of colored Petri nets and classical Petri nets, so just they coincide. And actually, like I was showing you folding classical Petri net to colored Petri nets for training philosophers, then for colored Petri nets with finite types, you can unfold it to classical Petri nets and then to apply different techniques. Of course, there are also some techniques which can apply directly to this more high-level variant, but of course it is not too much. So mainly it is used for either for model checking or for simulating. So when we can just construct reachability set. Proving something is possible, but not much, not so much. So that's what I was going to tell you, and now I'm ready to answer questions, comments. So you can, I didn't show you one more book I was to. So there is a book by Wolfgang Reisich, which is called Understanding PetriNet. It is a very nice book, very good introduction, very well written. Published by Springer, you can easily find it. And it is a good reading, explaining both modeling principles and how to do analysis for PetriNet. Well, if there are no questions, you can ask me any questions actually. So I can try to answer. Then thank you very much.